Yeah, sure.
Okay. Okay. Welcome all. It's my great pleasure to announce today's talk. Professor Ashish Gupta from our university will talk about the group determinant and the origin of representation theory. Okay, please go ahead.
Okay, great. Thank you very much for the organizers. Thank you very much, Stefan and Suresh and Shamit Paul. So it is, great pleasure to be talking in this seminar series. Now the topic we have chosen today, this is meant to inspire our young members, the students, to get some knowledge and feel of this wonderful paradigm in mathematics, which we call representation theory. So my aim is to give you, a glimpse of what this is and what this is about and what this deals with, so that it is just a kind of an invitation to this, more higher realms of mathematics. So, so this is a one door. Okay, representation theory is one door to get an understanding of this wonderful mathematics that is beyond the curriculum that we are offering in the master's program, or what if you are a PhD student, then what you have, the kind of curriculum that you have gone through in your master's program. So the terminology here, that is very basic. It is it deals with groups and determinants, and but these notions, this somehow they lie at the they herald the representation theory into mathematics. So what is this about? So let me begin with groups. So you know that groups was introduced by a young man who's called Évariste Galois. So, and he particularly found that there is a very nice way to answer this question about writing down formulas for the polynomial equations in one variable, and which equations. The question is that which equations you can have formulas which give the roots of the which polynomials, which degrees can you write formulas which give the roots of the equation. So you know the quadratic formula, you know the cubic formula, and there is also a quartic formula, which is defined in terms of the coefficients of the equation, and that that gives you the root, all the roots. So what this group entails is, Galois associated a group with every polynomial, and in some sense it is the symmetric group of a polynomial. So that's over with Galois. Now let's come back to Dedekind. So now Dedekind was, as you know, interested in number theory from an algebraic perspective. So he used to consider algebraic number theory, field extensions, and algebraic fields, algebraic number fields. So during his investigations, he found that there is a type of matrix. So this kind of matrix, we can see what is happening in this matrix, that this matrix has got, this is a matrix of variables. And these, how many variables are there? So we have a group, and we are enumerating the elements, and G1 up to Gn. And then we consider some commuting variables, xg1, which are indexed by the group elements. Okay, so perhaps for the students, I think perhaps it's the first time that you are seeing this kind of thing, that you have some variables which are indexed by the group elements. So, and then we can form this determinant. So what is this determinant? Let me call out the entries. So the first row looks like G1 inverse. Then second column, first row entry is G1 G2 inverse. And if you look at the first column, the second row, first column entry is G2 G1 inverse. So the general form of an entry, which is on the left hand side of this equation, you can see it is X Gi Gj inverse. So Gi is the, what is Gi? So I mean, the Ij entry is Gi Gj. Okay. So G1, G2 up to Gn, this is some kind of an enumeration of the group elements, and you are then writing down this matrix. So this becomes a matrix of these variables x1 up to xg1 up to xgn, right? So this matrix, you can see it's not difficult that the first row, first row contains all the variables xg1 up to xgn in some order. Okay, it can be x1, x2. It can be xg1, xg2. It can be, some other order also. So it depends on the group multiplication. So, and the second row onwards, you see what is happening. If you think about it, that these, you are going to get a permutation of the first row. Okay, you are going to get a permutation of the first row, and these are all. So all the rows, they contain all the elements of all these variables indexed by all the. So xg1, xg2, xgn. All the rows, they are sort of permutations of this this row. Okay, but the way. So this the idea behind constructing this matrix. This is very important, particularly because it is doubly indexed by the elements of the group. And so if you see the indexes, then the indices, they are doubly indexed. And they are also entailing a property of algebraic number field. So if you have a finite extension, Galois extension, and you take, if you write down the conjugates of an element, okay, so what will happen? That you will have so if you write down the conjugates of an element, then you have the Galois group is the indexing group, because conjugates, you're taking all the sigma x sigma. So suppose we have an element, let us say A, and we take sigma A, sigma 1a, sigma 2a, sigma 3a. So we are getting a sequence, a one-dimensional array, which is indexed by the elements of the group. Now, further to this, if we recall that, so suppose that instead of working for just one element, you want to do this thing for all the conjugates of this element. Okay, so instead of writing the, all the Galois conjugates for one element, you want to write that for each conjugate of that element. Then you will get elements of the form sigma I, sigma j of A. Okay, where sigma they are in the Galois group. So this means you get entries of a matrix which are doubly indexed by these by sigma I, sigma j. Okay, so this was the initial motivation. I think that you can see such determinants if you read even now in modern books also on algebraic number theory. You will come across such determinants. So that was the original motivation for introducing this kind of determinant from Dedekind. So now let's move further in the story. So Dedekind, as I said, he was led to consider a determinant with entries doubly indexed by the elements of a Galois group. So this G in this case was a Galois group. But then this same kind of, so what happens, let me show you that suppose, I just want to go a little bit ahead and show you for the group Z3, okay? So Z3, let us take A to be 1, B is the generator, and C is the square of the generator. So these three elements, they are all the elements in Z3. And then if we try to write down this group, the group matrix, where is the group matrix? So this is here. So what we are writing is that, the entries we are writing as theta, entries we are writing as x of gi gj inverse. So if we write these for this group Z3, then what we'll have is that we'll get this matrix XA, XC, XB. See, what will happen is that whenever you take an entry, let us say X, GI, GJ inverse. So GI and GJ, they are coming from the group. And therefore, GI, GJ inverse, that is also coming from the group. Okay, so ultimately what will happen is that you will get this matrix whose of variables whose with indices coming from the group. Okay, so this is what you will get, and you can check it. Any student who is interested can check. So, and this kind of matrix, we know, we learn in the competition books that this is factorized as this. Okay. So all the Olympiad books, they will contain this formula. So XA, XB, XC, and then this, and then this. So now one question that may arise to you is that suppose if I do the same thing for Zn, Zn will be the group, let us write it as A naught equals to 1, A1, A2 is equal to A1 square, and so on. So this group, for this, if you write this determinant, whose ij entry is x, gi, gj. So what is g1 here? G1 here is a naught, which is 1. Yes. So what will happen to G1 inverse? You will get 1, 1 inverse, which is again a naught. And what is 1, 2 entry? 1, 2 entry is G1, Gn inverse, G1, G2 inverse. So if you see what is G1, it is A naught, and G2 is A1. So what is G1, G2 inverse? It is 1 times A1 inverse. So A1 is chosen to be the generator here in this cyclic group of order n. So A1 to the n will be A1 inverse will be equal to A1 to n minus 1, and that is A n minus 1. Therefore, I get x a n minus 1 here. Okay, so this is how the variables will appear then in this form. And you can see there is a nice property of this. That all the successive rows. So you see the first row is coming as a naught, x a naught, a n minus 1, a n minus 2, and so on. So it gets decreasing up to a1, and then the successive rows, they are arising as cyclic shifts of this. So if you shift it cyclically, the first row, what happens is that this a1 goes to the first entry here, and then these all follow. Okay, so this is called. So what? So if we shift this, so if you move this, what will happen? That a1 comes here in the first column of the second row, and then all of them follow. Means a naught, a n minus 1, they follow. Okay, so this is an interesting way, cyclic shift to. So this is the group matrix, and then what is the determinant of this? Because I have put these bars about this matrix. So this means that we're talking about the determinant here. So the determinant, it will be not an easy thing to do, but if you manage to calculate the determinant, then you will see that it will be it will have this, it will factorize like this, okay? Where is it? So, yes, so here is the formula. You can see that it is factoring, this determinant is factoring into n factors, and each factor is given like this. Okay, these are all linear, these linear polynomials in these variables. It's not. So what I have done is basically that I have rewritten this matrix, which is for simplicity, where this matrix is xa naught, an minus 1, an minus 2. I have dropped out a, and I have written it x naught, xn minus 1, xn minus 2, and so on, xn minus 3. So giving that form, you see this determinant looks like this, okay? And then I claim that it factorizes like this, okay? So x naught, so there will be n factors. What is the first one? First one, I'm saying I is equal to 0. So all these exponentials at I equal to 0, they'll assume their value 1. So of course the first factor will be x naught plus x1 plus x2. So this is a, determinant, interesting determinant, and you can see that it factors like this. Okay. So what? What are the coefficients? If you see the coefficients, you see occurrence of the roots of unity in the coefficients. Obviously, what is this e to the 2 pi or n? That is just the nth root of unity. Okay, so these are the coefficients. Even if you go back to the case for Z3, you see that you have omega squared. What are these? These are cube roots of unity. You know, not that are not 1. So this there is this occurrence of roots of unity in the coefficients, and these coefficients are nothing but they are the characters of Zn. So what is the character? I think those students who are learning number theory, they must be already aware of characters of abelian group. So what is that? That you look at all the, if you have an abelian group A, you look at all the group homomorphisms from, a character is a group homomorphism from the abelian group to the multiplicative group of complex numbers. Okay, so if you have a cyclic group, then any homomorphism, so cyclic groups, the generator must go to a root of unity under any homomorphism. That's clear. Okay, so then how many characters you will have? Of course, for the generator you have n choices because they are precisely n roots of unity in C star. Okay, so therefore there will be n characters, and so you know that already before when the Dedicant used to work, already Dirichlet had introduced characters in so already he had introduced characters, and in conjunction with L functions, he could prove this theorem on the infinitude of primes in linear polynomials. So Dedicant was well aware of what is a character, and he immediately made note of this fact that actually he was able to work out this factorization for all these cyclic groups. Okay, which I showed you that he could write. He was the person who was first interested in this problem of this determinant and its factorization. So he could, he knew that so now he could prove that if you take any abelian group, okay, or whatever abelian group you like, you take a cyclic group, you take product of two cyclic groups, you take your favorite abelian group and you write down this group determinant for that. You will see that the group determinant will factor into linear factors like this. I'm showing you here in this equation. It reads theta of A is equal to this. Time is running really fast. So, Stephen, when have we started? Do you have any? I don't have any notion. When
we
exactly?
Started a little late, so we started maybe 5 minutes late, or even more, 10 minutes late or so. So take your
we
time.
started. Okay.
Yeah.
So this is thank you. So this is factoring into linear factors, and you can see that in the each of these linear factors, is obtained by one character. Okay, so you take I think that I mean, all the students who are very smart, they will realize that the characters of an abelian group themselves form a group, and perhaps they will be also I mean motivated to show that the order of the group of an abelian group is equal to the order of its character group. This is always true. Okay, so now during this period 1886 to 1896, so Dedekind was working over this for quite some time. Okay, so about 10 years. Okay, and Dedekind was in the senior stages of his career, so this means that he was, I mean, he was interested in this problem. So theta A, he said that this will factorize like this. These xg1, xgn, these are the variables, and the coefficients. Okay, coefficients. There is one factor, one linear factor for each character of the group A. Okay, so this is, and this proof is not very difficult. It just uses basic properties of determinants, which we learn in high school. But there is a clever proof. So he shows this. So now what he also showed that after he solved this problem of factorization for abelian groups, naturally his attention shifted to non-abelian groups. And what is the first non-trivial example of a non-abelian group? It is S3, of course. So S3, let us look at the situation for S3. So what do? We know that S3 has got 6 elements: 1, 1, 2, 3, 3 cycle, 1, 3, 2, 2, 3, transposition, 1, 3, transposition, and 1, transposition. So there are 6 elements in all. Now you label these 6 elements as G1, G2, G3, G4, G5, G6. You can see it's there on the slide. So, and then once you have done that, then you write the matrix X, Gi, Gj inverse, whose Ij entry is X, Gi, Gj inverse. You do that. It's not difficult. You know, anybody can do that. So if you write, you will get this matrix which is shown here. Okay. Now this matrix doesn't have that kind of symmetry. You know that if all the rows one after the other, they are obtained by cyclic shift. Okay, that kind of thing is not there. In fact, what I showed you earlier, there is a special class of matrices. It's called circulant matrices, where which we have seen for these cyclic groups. But here we don't see. So this is more random kind of matrix. Theta S3. Now, what is the order of this matrix? 6. And if we expand it, what will happen? The determinant. If we expand the determinant, what will happen? We will get, everybody will agree with this, we will get homogeneous polynomial in these variables x1 up to x6 of degree 6. Okay, so so there is a highlighting in these slides. I should use it. So theta S3 is this determinant, and now Dedekind found, because he was an excellent mathematician, he found that theta S3 factorizes as a product of 3 factors. You know that because in any number of variables, so we are considering here factorization over what? The complex numbers. We are looking for factorization over the complex numbers. Means that the irreducible factors that we get, they are coming from the polynomial ring in 6 variables over the complex field. Okay, so he found that this theta of S3, it has got 3 irreducible factors, What are these three reducible factors? They are phi1, phi2, and phi3. Phi1 is this factor which is the sum of all these variables, and phi2 is x1, x2, x3 minus x4, x4, x6. Phi3 is a more complicated polynomial. It's a quadratic, it's a degree 2 homogeneous polynomial. It is x1 square, x2 square, x3 square minus x1, x4 square minus x5 square, like this. And then there are these mixed terms, x1, x2, all these terms. So it's a very strange kind of, it's a quadratic and degree 2 polynomial, right? And it occurs to degree 2. It occurs in second degree, second power, okay, in this factorization. So now this interested Dedekind very much. So what he thought that that up to now, when he considered the abelian groups and when he wrote down the group determinant for that, he saw that the group determinant always factored into linear factors. But this, for the first non-abelian group, he found that there is a quadratic factor. So what he thought then, that this quadratic factor is coming because he is not working in a sufficiently high system. So what I should tell you is that in those days, these fields, what we call fields, they were called number systems, okay, probably. And the number systems, so complex numbers is maybe it was called complex number system. And then at that time also, you know that it was already Hamilton had already lived before Dedekind. So they were also aware of the quaternions, okay. So quaternion is, in those days, quaternions and octonions, all these things, they were called hyper complex systems because they are even higher than complex numbers. Means that, you know, that Hamilton's quaternions, it contains a copy of the complex field, okay. So therefore they are higher than complex numbers, but they are non-commutative. That is very well known. So, but his view was that if you consider the factorization over these hyper complex numbers like quaternions or octonions, then this should factorize, the group determinant should factorize into linear factors. But he tried his hand at that. So what he found, that if you take the quaternion group, so quaternion group, you know, that is an order 8 group. I think most of the students know the definition. So that group, if you take the group determinant of that group, then Dedekind was able to show that this group determinant, it will factor into linear factors. Okay, it will factor into linear factors, with provided that you allow for the coefficients to come from the quaternion, from this field H, skew field. Okay, so if you allow, so you know this skew field H has got, C has got as basis over R, it has got 1 and I. H has got as basis over R 1, I, J, and Ij. So if you allow the coefficients to come from H, then he could show that the group determinant of the quaternion group also factors out into linear factors. Okay, so now Forbinius, you know, he was a great mathematician of 19th century. I mean, at the same level as Dedekind, and outstanding mathematician. So Dedekind had some kind of a correspondence with Forbinius, and he wrote about this problem to Forbinius. So it immediately caught Forbinius' attention because Forbinius was interested in both the groups. You know, there are groups called Forbinius groups. So he was interested in groups. He was also interested in determinants. So therefore, this problem interested him very much. But so there is this phrase that is attributed, attacking the problem from all possible angles. Okay, So this from this the letter of dedicant threw him into a period of spirited activity, attacking the problem from all possible angles. Now, so um, but there was a, a difference of viewpoint. Frobenius was not so much interested in this problem of finding this. So what Dedekind wrote to Frobenius was about, for any group G, how can you extend this complex field? I mean, go to some higher system, higher number system, that over which the group determinant will factor into linear factors. But what interested Frobenius more was this factorization over the complex numbers itself. So he was not interested in. So if you go back and look at this factorization of theta S3, what Frobenius found interesting was this factorization itself. He was not so interested in what Dedekind was, that how can we factorize this phi 3 into linear factors. This phi 3 is a quadratic homogeneous polynomial. So he was not that much interested in this. He was interested in this very factorization. How does one explain this? Okay, so he was also aware of characters. Okay, Frobenius, but before Frobenius, there was no notion of a character of a non-abelian group. Okay, there was no notion of the character of non-abelian. So I've told you for the abelian groups, what it means is that characters are basically group homomorphisms, means a multiplicative maps from the group into the multiplicative group of complex numbers. These are characters, okay? And but for a non-abelian group like S3, what should be what is the definition? Nobody knew. What is a character? Nobody had talked about, nobody had defined. So there was no notion. Okay, so now I have left aside for the moment the methods into which Frobenius used. So I mean, as you would expect, that this problem that so it was a triumph of Frobenius that he solved this problem. Okay, what Dedekind wrote to him about the factorization. He solved this problem, and the methods that he used, that were mainly based on matrix theory, okay? But I want to, bypass those methods for the moment, because I want to talk about representations, okay? Because, I talked already about the reason for this, I already talked about. So what is the representation? So this is something which you see very often, okay? As you will read more and more mathematics, you will see more and more often that you are having a group G, okay? And now for few minutes, even if you forget about what I told you earlier in this talk, that's fine, okay? I just wanted you to think about what I'm telling you now. That if you have a group G, now you will see often it happens that there is a complex vector space. It's fine, right? It can be any other field also, but that's also fine. So you have a vector space, and a group is acting on that vector space, okay? Group is acting, all of you know, you have learned in algebra course what is the group action, I'm sure. So, and that means that G, there is a map, there's a homomorphism of, so action of the group there are some axioms, and they are precisely equivalent to an homomorphism of groups from G to GLV, okay? So it is not, this idea is not something that is made up artificially. The idea is that it occurs very, very often. So that you find that whenever you, many different fields also, that you have some vector space and there is a group which is acting on this vector space. So, and then there are some fundamental notions, okay? What are these fundamental notions? Invariant subspace. So I'm sure that all these notions that I'm going to talking about, most of the people here, they are already aware of that. They have come across it one time or the other, but this is just recalling these. So What is an invariant subspace? So you will see that inside U, I mean subspace of U, subspace U of V, okay, such that it is stable under the action of G. Means if you take an element from that subspace, any element of G will move that element to some other element of the same subspace. So this is invariant subspace. So this idea is also, most of you should be familiar now. Clearly, now, but now we are using this terminology of representation theory. So let me define this term. If you have an invariant subspace, then that defines a sub-representation of V, because that allows an action of allows for an action of G on GLU. Okay, simply because it is invariant. So this is a sub-representation. Means that you take out the subspace of V, which is also affording a representation of G. Which is also on which G is again acting. Okay, so that's clear. That's very natural. So now minimal invariant subspaces, those which cannot be. You can have this subspace which is invariant. Then again there is subspace inside that subspace which is invariant. So this can go on, but there you can also reach such an invariant subspace which is minimal, means that it does not properly contain any invariant subspace. Okay, this is also very important notion in this theory that I'm talking about, that it is minimal, means that invariant, it is invariant, but at the same time you cannot again find an invariant subspace. Okay, so now I'll give you an example. Suppose that group of the triangle, equilateral triangle, this is D3. Suppose D3 acts on the plane R square, then what happens is that one of the elements of D3 is reflection, one is rotation by 2 pi on 3. So when this D3 acts, you know that there in this plane, which is, you can take R square, okay, the real plane, and in this R square, there is no line. Line means a proper subspace of R square, which is stable under this group, because, a line, the rotation will rotate it. It's possible that a line is invariant under reflection, if it's the, but it cannot be stable under rotation. Therefore, that is a minimal, that is an irreducible representation. Means that you cannot reduce the representation still further, okay, by passing to a invariant subspace. So, this is like a fundamental cell, okay, of this representation. So, okay, but these were all very, you can have your. So now representation means. So I've talked about this. And this has another very interesting viewpoint. What is that viewpoint? That we all know what are modules over a ring. Okay, all of us learned that. So this representation, which I have said that this is just a homomorphism from G to the general linear group, means all the invertible linear transformations of a vector space V. This has another viewpoint. You can. There's an alternative way to, alternative equivalent way to view this. What is that? That whenever you have a group, you form a ring. Okay, how do you form a ring? That you just take the linear combinations of the group elements with coefficients coming from the field. Okay, this C is complex numbers. So these alpha G's are coming from the complex. These are complex numbers. And what I have written here, if you see this equation, that I have written a way to multiply two such linear combinations. So what is happening? That CG, this CG is a ring. It is defined as all possible linear combinations with coefficients in the complex field of the elements of the group. And there is a way of multiplying this. How? That just as you multiply polynomials. When you multiply polynomials, you see that they are also linear combinations. Okay. And then if you multiply, you first multiply term by term, and then you combine the coefficients of like terms. This is exactly what you do when you multiply two such elements. Then you are also multiply. So you will multiply I mean, if you term by term, then you will see that you will get terms like alpha G times beta H times H. Okay, so their product will be alpha G beta H times GH, and GH is again an element of the group. So I've written it here actually. So what happens is that you find H and K are group elements, and you find that if you multiply the two terms alpha H times H and beta K times K, if you multiply them, you get alpha H beta K times HK. Now, if your HK is G, then this this term will become alpha H beta K G. And then as you do it for polynomials, you combine all the coefficients which appear for this, all the coefficients which appear in this multiplication of the element of this group element G. Okay, so this is not very difficult business. It's not very advanced. Any of you can easily understand this. So this is called a group ring. So what happens is that what you have basically done is that you have basically the idea is that what is the idea behind this group ring? Let us come back to this homomorphism rho. So this homomorphism, as I said, that this is a map from G to GLV. So you are having a so this is just saying that elements of G are acting on V, but V also a priori it is a vector space over complex numbers. So scalars from complex numbers are also acting on V. So in this group ring, what you have done, you have tried to bring together these two in a harmonious way, these two actions, one of the complex scalars and one of the group, and then so what you make of it is that the representation, this action, what you have written here, is equivalent to a CG module. So this CG is a ring, and so what what this notion, what it does is, you can, this is equivalent to saying that this this representation, this map, this is equivalent to V becoming, this V becoming a module over the ring CG. Okay, this also, if you see some books on this topic, you will be able to see how this happens. So okay, so let me tell you one thing, that how do you get the module structure. So once you have got this ring CG, then what do you do, that how do the elements of CG look like? They look like sum over G, alpha G times G. And then if you want to act it on an element little v from the vector space, you define the action like this. Okay, so notice this carefully, this white line, that you let rho G is, so rho is the representation, which means that it is this map going from G into GLV. So rho G means that the linear transformation that corresponds to this element G, that linear transformation acts on V, this little v, which comes from the vector space capital V, and then the scalar also acts, this alpha G. So, and then you take the sum. So this is how the element from the group ring acts on the element V, and that action makes it into a module. So these things are equivalent, whether you view a representation as a homomorphism from G into GLV, or you view it as a module over the group ring. They are one and the same. Okay, so this is what I've written, that actually what is happening is that, see, for each element of the group ring, which is this, you are getting this element of the group ring is acting as a linear transformation. Why? Because rho G is a linear transformation, and alpha G, you are taking linear combination of linear transformations, which is again a linear transformation. And where does it belong? It belongs to NCV. NCV is the ring of the linear transformations of V. So what, this, if you want, I can share the slides if any student wants. So you can, in your own time, see that how you are getting this map from the group ring into the ring of linear transformations of V. So let us move further. So now this, So what is this concept we discussed earlier? We said that this representation is irreducible. That means that we don't have any invariant subspaces properly contained inside this space. That concept becomes the same as the concept of a simple module. So if you have any notion of modules, you know that modules can have submodules, and submodules in this context correspond to sub-representations. So if you have a module which is simple, then that is equivalent to the representation being irreducible. Okay, so now I want to recount two basic facts, fundamental facts from representation theory. And if you just take note of these two facts, it is enough for most applications. So what are these facts? One is called Burnside's lemma, which says that this map rho hat that we are getting from CG to NCV, okay, this is a surjective map. Means that you know what is, so that every linear transformation of V arises in the image of this. So you know this rho hat, how is it defined? That you take an element of the group ring and you, it is of the form alpha G G sum, and you map it into alpha G times rho G. This is a linear transformation. This is linear combination of these linear transformations rho G. So this is map and this is surjective. So this is called Burnside's lemma. And then there is another important fact which is called Mashka's theorem. So what is Mashka's theorem? That it says that this CG module, each CG module n is semi-simple. But that it means that it is uniquely a direct sum of simple submodules. So what is this? I mean, you know that how vector spaces, they can decompose into direct summands. All the students know this. So what happens with this CG module V? V is a representation that it splits, always splits. This is a theorem. It's called. There's a lot of algebraic theory behind this, so like the semi-simple rings and all this ring of theory of semi-simple modules, semi-simple rings. And so what it does is so it splits. So it says that any representation, any module will split up into direct sum of these V1 up to Vs. Okay, in fact, there are more than that, because I've taken that it's further splitting into V1, D1 copies of V1, D2 copies of V2, and so on. So what it means is that every module will split up into this irreducible, all these Vi, V1 up to Vs, they are all irreducible, they are minimal invariant subspaces. So this will happen for every representation, no matter what representation you take. And they will, and what you do is that when they split up, you bunch together the isomorphic ones, so isomorphic, sub-representations, and then you combine them, and you see that, these V1 V up to Vs, they are non-isomorphic, pairwise, and then you have grouped them like this, okay, with multiplicities. So the lot is known. If you read about representation, you will look through some elementary books like Artin or Winberg or something, then you will see that this is the basic material that tells you a lot about these multiplicities and all these things. So anyway, but this is enough of this technical stuff. But now what I want to talk about is some concrete examples where you will see representations arising in the so suppose that there are 4 cities. So 4 cities, they are located on the vertices of a square. So, and suppose you want to build a network, road network, which has minimum cost between these 4 cities. How will you build a network? Like this, okay? You see the first, this has got 2 pictures. You see the first one. The first picture is showing a road network of minimal cost with joining these 4 cities, okay? This angle is 120 degrees. So this you can prove easily using calculus or something, that this is indeed the minimum possible way of constructing the road network. Now, what I want to say, so I have introduced this, rather abstract notions, representations, and all these things, but I need to justify how does this notion of representations comes in real life. So, the idea behind this is that if you have a problem, Okay, mathematics is about having problems and solving them. So what is the suppose that you have a problem, and the problem is that build the minimum cost road network between these four cities. So when you solve that problem, you solve it using calculus, maxima, minima, something like that. I mean, you are all very smart, so you know lots of ways. Maybe some geometric also, maybe algebraic topology. You know lots of ways. But the point is that this problem has a symmetry. What is a symmetry? That these cities are on the vertices of a square, and a square is a symmetric object. We know its symmetry group. It is D4. So what the problem has a symmetry, so must the solution. This is natural to expect that if your problem has a symmetry, then I mean the problem, these four cities, if I apply any element of D4, what it does is it rotates these four vertices. So the solution should also have that symmetry. So what does it mean? That we have an action of D4 on the space of solutions. Means that D4, suppose D4 acts on this square. Okay, I have not drawn this square, but suppose you draw a square, joining these four vertices with these four cities as vertices. Then what happens when D4 acts on this square? Suppose it, rotates this square, so by 90 degrees. Okay, then the solution becomes this. The road network becomes this. And this is also a minimal cost solution for a minimal cost road network. Okay, both are minimal cost network, but we discovered this second one by applying the symmetry group of the square. Okay, let's look at another example. Suppose I take this differential equation. Okay, so what is happening here? This is a differential, and suppose that the coefficients, these are AIT, they are periodic functions with period 2 pi. Okay, so if ft is a function which is a solution of this equation, then you would expect that ft plus 2k pi is also a solution. Okay, so what is happening here? The problem has a symmetry. What is symmetry? That it is invariant under translation by 2 pi, and therefore the solution also has a symmetry. So what happens that this if ft is a solution, then ft plus 2k pi, it is also a solution. And for k integer k. So what is this giving us? It is giving us a representation of z, because if you have k belong to z, then you know that k takes this. So the space of solutions will be a vector space, and any integer k acts on this space by taking ft to f of t plus 2k pi. So this is a representation. Okay, so I will try to give you more examples, but they are very interesting examples from physics if I have time. Okay, and so I will try to give you. So now, so let us come back to. I think I have around 10 minutes, or if Stephen allows me, maybe 15 minutes. So I will talk about the solution of this problem. Okay, using this representation theory concept. How to factorize theta g for any group. Okay, so this looks a bit technical, but don't worry, I will explain you. So how do you solve this problem using representation theory? So as I said, that Forbinius invented representation theory. From his studies came out this new branch of mathematics as we know it, representation theory. So representation theory as we know it, but he didn't use these methods. But let us see, how this representation theory answers this problem of the factorization. Okay, so the idea is very, very simple. I think it will take me 2 minutes to explain it. So you look at, you come back to this these variables xg. Okay, one for each element of the group. Now what you do, you take a representation of the group. Okay, and you write this operator. This is, operator valued polynomial, which is xg rho g. What I'm doing, that rho I'm fixing to be a representation of the group, and I'm considering this operator valued polynomial, which is xg sum xg rho g. So what will happen to this, that if you give specific values to these variables xg, then it will give you a specific linear transformation. So this xg rho g, okay, rho g is, what is rho g? Rho is the representation, so it's a map from g into some glv, and what so see, what we are aiming at is the group determinant matrix, the group determinant, the matrix that we started with, okay, is actually the matrix of this operator, which is this operator xg rho ig, xg rho g, okay. So I should go to this, back to this. Yeah. Okay. So consider this representation of G. Okay. On what space? On the space CG. Okay. CG is also vector space. What is CG? That it's a vector space whose basis is the elements of G. So G1, G2 up to Gn, if you want, then this is a basis of this vector space CG. And you consider, and you make this, you take a representation of G on this vector space, which is called regular. What does mean by regular? It means that it is the most obvious kind of representation. What is that? That if you take an element G, if you pick an element G from the group, then that group, then that little g acts on this CG, the space CG, by left multiplication. Okay, so I will give you this white highlighted part, this telling you this, that if you have this operator valued polynomial, which is sum xg rho g. What is this sum xg rho g? This is just a transformation. Okay, this is just transformation. When it acts on H, what it is, so you see the representation here is the so it doesn't matter. So what is the space? Space is CG. Okay, CG, it's a space whose bases are the elements of the group. So to determine the matrix of any operator on this space, we need to write down its action on the basis elements. If you take any H from this group G, okay, H is, so now basis elements of CG are the group elements. So if you take H to be in a group element from G, and if you add this operator on H, then what do you get? Xg rho G of H. What is rho G of H? By definition, this is the regular representation, means that elements of the group are just acting by left multiplication. So this becomes xg times gh, and g, the sum g over g, and that you can rewrite it as, so this xg gh, that you can plainly write it as, because the gh will range over all the elements of the group as g ranges over all the elements of the group. So this is the same thing as x g h inverse g. Okay, so means that the index of this variable gets shifted. Okay, this is now, if you add this operator valued polynomial on gi, so gi, you know, gi is the indexing of the group elements, which comes in the group determinant. So if you act it on gi, then you get some xg times gi, and that is xggi inverse times g. Okay, so I mean, this is where this ggi inverse, this means this is a hint to us that how that group determinant arises. That arises from as the matrix of this operator valued polynomial, with respect to the basis G1 up to Gn. Okay. Gj, then you get Gj Gi inverse. Okay, and here if you put instead of I you put J, and instead of G you put Gi, then you get Xg I Gj inverse. So this is how that matrix of Dedekind that will come from this regular representation. And now let me very quickly come back to a very elementary fact from linear algebra. So this I've already told you that the regular representation, which just means that the group G, which is basically obtained by letting the group G act on the space CG. CG just means linear combinations of elements of G with coefficients from C. So if that is the space, then this regular representation amounts to the regular module over a ring. Okay, what is a regular module? That if you take a ring, you can regard the ring itself as a module over itself by letting the elements of the ring act. Action of the elements of the ring is just the multiplication of the ring. You just take the multiplication of the ring to define the action of the scalars in that for regular module. So it's so the regular module, by I've already told you this a few slides back, that any module over the group ring that will split up into a direct sum of submodules like this, irreducible submodules, simple submodules. Okay, simple submodules, it will split up like this. So so this means that this space CG is decomposed like this into irreducible representations, V1 up to Vs, and T. What is T? T is any linear operator on CG. Okay, if T is any linear operator such that each of this Vi, this is invariant under T. Okay, so what will happen is that that determinant of T, so suppose that T is a linear operator on CG such that each Vi is T invariant. Then what will be the determinant of T? That will be the product of the determinants of these, the subspace T restricted to these subspaces. So you will get determinant of T is the product over I of determinant of T restricted to Vi and to the power of Di, because this Vi is appearing to the power Di. So this is just linear algebra. But now T we are taking to be this operator which I am talking about, this operator. Okay, so how much time left? Seminar organizers, please.
In fact, you have talked about 1 hour now. Yeah.
So it's over.
Okay, the time is over, but you can extend maybe 10 minutes or so.
Okay, so 5 minutes. 5 minutes, is that okay?
Okay.
So now this, yes. So if you, for T, if you take this operator, which I have been talking about, where is it? Yes, this operator. This xg rho g. Okay, xg rho g. So rho we have fixed to be the regular representation, means that G is acting on CG by this left multiplication, and G varies over all the elements of group, and the operator T is supposed to be the sum xg rho g. And already we have noted that if we take its matrix with respect to the space CG, then we get the group matrix. So by this formula, the determinant of the group matrix, which we are calling theta g, it should be equal to the product of the determinants of this operator xg rho I g. Rho I, I've written rho I because rho I refers to the sub-representation of G on each of these invariant subspaces V1 up to Vs. So I mean that because they are supposed to be invariant subspaces, okay, they are invariant subspaces for this regular representation. Therefore, rho, the regular representation, of G will restrict to a sub-representation on each of these subspaces, and which we are calling rho I. So rho I is nothing but it is G acting on each of these. So G acting on each of these subspaces, it is invariant, so it will again give you a sub-representation, and you just take the determinant of the matrix of this operator. Okay, so that will what give you. So when you think about the matrix of this operator, you will see what is xg, what is rho ig. Rho ig, suppose we fix a basis of this vi, then rho ig for each I, that is just a matrix of complex numbers. So what is this sum over G of xg rho ig? It is some matrix whose entries are linear forms in these variables xg. Linear forms means that it's some linear combination of these x1 up to xn, these variables, xg1 up to, these variables xg. Okay, so if you take the determinant of this matrix whose entries are linear polynomials, then what you get is you get some degree di polynomial. Okay, because the determinant, so because this matrix has order di, so the determinant will be a homogeneous polynomial of degree di. So this is what accounts. So this is now how this group factorization of the group determinant is taking place. Yeah, this is the last line. So yes, this last line is saying that that this theta g is is decomposing as product of fi degree fi. Okay, so this is what representation theory is telling us, that because what is known, I told you that you can see some books. What is known is that if you look at this decomposition we had for CG into minimal invariant subspaces, this one in the box, then we know from basic theory that the multiplicity of each vi, this di, that is the same as the dimension of vi. So this is a very nice thing, that whatever is this dimension of the space vi, the same will be the multiplicity with which it occurs in this decomposition. So as a consequence, this decomposition is arising just when you restrict this group this operator, polynomial valued operator sigma xi sigma xg times rho g. If you restrict it to this, to these minimal invariant subspaces, you get the factorization. And we have also used one fact here, that if you have algebraically independent variables, then the determinant of a matrix which has got algebraically independent variables, it is irreducible. Okay, so all the students should prove this, that if you have a determinant of algebraically independent variables, it is irreducible. You can see it with just 2 by 2 determinant. If you have x1, x2, if you take x1, x2, x2, x1, what is that? X1 square minus x2 square. That is irreducible polynomial. So no, algebraically independent variables means that x1, x2, x3, x4, 4 variables. Take the determinant, which is x1, x2 minus x3, x4. This is irreducible polynomial of 4 variables. So this is the the factorization of the group determinant. It is fi degree fi. This is how representation theory explains it. And just going back to the S3 example, okay, just concluding my talk. If we go back to this S3 example, what Dedekind found, this you can very well explain from representation theory. See, if you look at the first factor phi1, this is coming from the trivial representation of S3. All the coefficients are 1 here. If you look at phi2, it is coming from the sign representation of S3. Means you take a permutation and you associate it with its sign. So that is the sign representation. These coefficients are 3 from 3 minus 1, 3 plus 1. And similarly, this phi3, this is coming because S3 has a 2-dimensional irreducible representation, which is because it is just D3, it is a representation on the, it is a 2-dimensional representation also. I mean, which is the symmetry group of the of the of this triangle, equilateral triangle. So B3 acting on the plane, I think it is. So that will give you a two-dimensional representation if you extend it to complex plane, irreducible representation, and this polynomial is coming from that representation. Again, you can, I mean, so that's all. Thank you very much. So the whole essence of this is that using representation theory, you can explain this to a good extent. You can explain this representation, this decomposition of the group, this factorization of the group determinant using this idea of representation. But as I said, that this has applications to many areas. So that's all. Thank you very much. I'm really sorry for going a little bit ahead of time.
No problem. Yeah, thank you very much for this very nice introductory talk. Yeah, giving an introduction into representation theory, and it's very valuable to have some historical background also. Yeah, are there any questions? Or comments?
Okay, so I have a simple question. Yeah, can you hear me?
Yes, yes.
Yeah. So let us look at the real question asked by Dedekind to Forbinius. So whether there really exists a hypercomplex plane or whatever you are saying, that this theta g will factorize into linear factors. I mean, is this question has been answered yet, or is it still open?
Actually, this question has, I mean, there is not too much discussion about this question after that. I mean, it has not taken a very prominent place. Maybe it is that some people have ruled out the existence of such hypercomplex systems. Okay, where, you know, for a given group, that group determinant will factorize into linear factors. So because this, I mean, this factorization over the complex numbers, that itself has taken up the, I mean, prominent role, because it can be, you know, I mean, it can be explained by representation theory, and it has come to be regarded as the origin of representation theory, because was precisely this problem is, in the solution of which Forbinius introduced a lot of ideas which have now become you know, key I mean, which are now central to representation theory, the modern theory of representations. But this question, it is not, I think that I may not be aware, but some people may have answered it. But personally, I think that it is not true that you can always find a hypercomplex system for which, I mean, every group will have a factorization into linear polynomials. So you can also think it's an open question.
Yeah, I mean, you can always replace this field with K. I mean, why look at the hypercomplex field? Sorry, hypercomplex system. So you can ask these questions for any other field K, because then you can always define the characters and carry on the same method, right?
You can ask this for any field K. You mean that you are trying to factorize the group determinant over some other field?
Yes.
Is that what you're asking?
Yeah.
So, I mean, the point is that the coefficients that appear here in this, I mean, for the factors, okay, for the irreducible factors, the coefficients which appear, they are related to the characters, the complex characters of G.
Yes.
You can actually obtain all the irreducible characters of G, any group, okay? Not any group you can obtain by looking at the coefficients of the, I mean, this irreducible factors of this group determinant. So, I mean, if you try to factorize it over any other group, then the problem will be that if it's not algebraically closed, I mean, you can factor, okay? You can factor because, I mean, So, for example, for the symmetric group, you can see that in this factorization for symmetric groups, the coefficients are only, rational numbers. They are all integers.
Yes.
Right?
Yes.
So, this kind of factorization is actually what happens at the, it's basically to do with the splitting. Okay. So when you have this semi-simple decomposition, right? The
Okay.
semi-simple decomposition is only valid if there's a splitting takes place. What is splitting? That actually the in this semi-simple decomposition, yeah, that will be not. You have. So you know that when I talked about that semi-simple decomposition, I said that each irreducible factor will occur as many times as its degree. I said that, right?
Yes.
So that property will not apply for any general field, because that depends upon the fact that in general, what do you get? So that will not hold in general, but for specific groups like the symmetric group, it can happen that over Q, because we know that the symmetric groups are split by Q, which means that that's in this decomposition, this degrees will match with the dimension. Even if you take even if you work with Q, means that if you work with Q's, if QG, the group algebra over Q, right?
Okay.
Then still the splitting will take place. So for the symmetric groups, but for general groups, what you will lack is that you can still talk about such a decomposition and factorization for other fields, but in that case, you know that I think you have learned this thing, that this dimension will not match with the degree of the polynomial. So I mean to say that the number of times this polynomial occurs in the decomposition may not be equal to its degree. Here, for complex field, you've already seen in the case of S3 that the quadratic factor is occurring with multiplicity 2. That is because it is quadratic, right? That is the point. That is the answer.
Okay. 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 Fine.
Okay. Thank you. Are there further questions or comments? Maybe you can send the slides, then we could distribute them, and if other questions come up, then
yes, in a couple of days, because I noted that there are some misprints in the slide. So in a couple of days, I will send you a revised version if any of the students are interested in going.
Okay. Okay.
A very nice talk, Ashish. Really enjoyed it.
Thank you very much.
Yes, it was very beautiful, and maybe motivates students to look into representation theory, which is a very important field throughout mathematics, also on number theory.
And once you get the slides, maybe I would also like to have a copy of the slides.
Yeah, I will send it to all. Yes.
Everyone. Okay. Good.
Okay, thank you very much to all. Thank you so much. Have a nice evening. Bye-bye.
Okay, thank you very much. Let's thank the speaker. So now he is already left. Okay, good. Yeah, so there will be a longer gap now in the second half of June, because we have the student presentations, project presentations. We will take up the colloquium again at the beginning of July. First speaker will be Peng Gao from Beijing, a number theoretical talk, but I will announce that in due time. Okay, so then have a nice weekend, and see you soon. Bye-bye.